So in the last few videos we talked about the completely randomized design, and in this video we will extend the notion of a random design to randomized complete block design. So we'll define and motivate the need for a randomized complete block design and draw on our knowledge of two-way ANOVA to conduct a randomized complete block design. And the next video will be going through a problem in R and doing the analysis on a real set of data. So blocking is a technique to include other factors in our experiment which contribute to undesirable variation, and typically these other factors are called nuisance variables. And blocking techniques can be used in experimental designs to control sources of variation that will reduce error variance, which is something that we always want to do. So if you recall, in a completely randomized design, treatment levels were assigned to experimental units so that each experimental unit had the same chance of receiving the treatment. And so that'll be different in a randomized complete block design, or RCBD. Units are first split into blocks, and then treatments are assigned at random within each block. So consider an example, an experiment about online advertising. So you've got a company X, and it performs experiments to compare effects of 4 different advertising campaigns for improving click rates on their advertisements. So suppose that the company shows each of 4 advertising campaigns to 3,000 people each. So that's 12,000 people total that will see advertisements. But the company notices that the ads were hosted by 3 different social media platforms. So in this example, which is similar but importantly different from the example used in an earlier lesson to illustrate the difference between an experimental unit and a sampling unit, the response is the number of clicks, and the treatments are the 4 different advertising campaigns. But in this case, if we suspect that social media platform that hosts the advertisements might have some effect on how many clicks each ads get, then we should record that information and use it as a blocking variable. So here in this diagram, I have illustrated what the 3 different blocks are. So in this example, it should be the 3 different social media platforms. Maybe that's Facebook, Twitter, and Instagram. And then within each block, within each social media platform, we would have 1,000 people, and among those 1,000 people, we would randomly assign. We would have 4,000 people, and among those 4,000 people within each block, we would randomly assign 1,000 to add 1, 1,000 to add 2, 3, and 4, etc. And we would do that within each block. So the random assignment is not overall among experimental units, but it's randomly assigned within each block. So the following table can help us decide when it's prudent to block. And blocking occurs with respect to nuisance variables. And nuisance variables are variables that might have an effect on the response, but aren't of primary interest. And so we'll see nuisance variables can either be known or unknown, and then controllable or uncontrollable. If the nuisance variable in question is known and controllable, then we should measure it and use it as a blocking factor. So in the previous example, social media platform was one such variable, right? We didn't care about social media platform explicitly, except that we thought that there might be variation across platforms. And so it's a known variable. It's something that we can control, and so we should block for it. So if the nuisance variable in question is known and uncontrollable, then we should measure it and adjust for it, say by using ANOVA. And for example, we might not be able to control when the ad is seen by the user, so the time of day, but perhaps we can measure the time of day, and in that case we could add that continuous predictor to our model and adjust for it, even if it's something that we can't control. So randomization is the ingenious solution for unknown and uncontrollable nuisance variables. Now, by randomly assigning the treatments to units, we can reduce the effect of unknown nuisance variables that might be correlated with the response. And so finally, if the nuisance variable is unknown, then of course we can't have any control over it, and so there's nothing we can do about those situations. All right, let's think about the mathematical model for the randomized complete block design. So we've now seen that if we have a completely randomized design with one treatment factor with potentially many levels, we can use the one-way ANOVA to analyze the results. Now, for a randomized complete block design, it should not be surprising that we can use a two-way ANOVA for the statistical analysis, with a treatment factor and a blocking factor, and each of those with potentially many levels. Of course, if we had two different treatment factors, each of potentially many levels, and a blocking factor, then we should need to use a three-way ANOVA, but we won't cover that in this course. So let's just remind ourselves of the two-way ANOVA model and couch it in terms of the randomized complete block design. So suppose we have a treatment factor tau, it has t levels, and a blocking factor alpha with r levels. Then the two-way ANOVA model will be yij, so that's the value of the response at the ith level of tau and the jth level of alpha. And that should be equal to the grand mean plus tau I plus alpha j plus epsilon ij. Right, and so we've written this down before, so I'll just mention, I ranges from 1 to t, and j ranges from 1 to r. And epsilon ij, of course, is the error term, normally distributed, zero mean, constant variance. At least those are the assumptions, and we know how to check whether some of those assumptions are not met. And so remember, in this design, the treatment levels are assigned randomly within a block, and the reason for this is to try to cut down on error variance. And we'll see exactly what this means in the next video when we look at some real data in our code. All right, so it'll be important for us to look at the ANOVA table to try to understand whether the treatments are significant and whether the blocking factor is significant, although if we're including it, the blocking factor should be significant. So if we fit the two-way ANOVA model in R using the LM function and then print an ANOVA table, we'll see something like this. And it's important to understand each cell, and especially important to know what tests are being performed with the p-values in the rightmost column. So let's sort of start from the right and be clear on what tests are being performed over here. So if we look at the row labeled block, and we go over to the column for p-values, this cell will test whether the blocking factor is at all significant. And so the null hypothesis will be that neither factor is necessary. And if the p-value is small, then you reject that null hypothesis and you conclude that just the blocking factor is necessary. So it's comparing the most reduced model of no predictors, no factors necessary, to just the model with the blocking factor. Now, most of the time, this p-value is not really of importance because you included the blocking factor based on, pre-experimental knowledge about the fact that the blocking factor is important, right? It controls variability. But the next p-value is important, and it will tell you whether the treatment factor is necessary. And so the null hypothesis is that the treatment factor is not necessary, but it includes the blocks. So the reduced model for this test would be that the blocking factor should be included, but the treatment factor should not. And then the full model in this case would be that the blocks are included and the treatments are included. So if you think back to our study of regression and the types of tests that we conducted on regression models, then you should have a sense of what sorts of tests we should use here. They should be F-tests because we're testing the difference between a reduced model and a full model. And if we're conducting an F-test, then we need to have ratios of sums of squares divided by their degrees of freedom. And so that's why if we look to the left in this table, we need degrees of freedom, sums of squares, and the MSE, which is what we call the sums of squares divided by their degrees of freedom. So I think what I'll do in this video is fill in maybe one of the rows and then see if you can fill in the rest, and then I'll post these notes with each row filled in. So to write down the sums of squares, we'll need a bit of notation, and so let's write down some notation along the top so that we can write down the block sum of squares, degrees of freedom MSE, and the F statistic, and then I'll leave the rest to you. So if I write y dot j bar, what I mean by this is the mean of the jth block across treatments. So how could we write that down mathematically? So I want to write, we're going to sum from I equals 1 to t of the response yij, and then we're going to divide by t. So j here is fixed at one of the levels of the blocks, and we're summing over I. All right, and then when I write down y dot dot bar, here all that I mean is just the grand, the estimate of the grand mean. So that would be the sum over I from 1 to t, and the sum over j from 1 to r of yij, and then we're going to divide by the total number of units, n. So when I write down the block sum of squares, the label that we'll use for it will just be SS blocks. And what that will be is the sum from j equals 1 up to r of t times that mean of the jth block across treatments minus the grand mean squared. Alright, and the degrees of freedom here should be r minus 1. And then we said, well, the MSE column, what I mean by that is just the sum of squares that we wrote down over the degrees of freedom. And then we'll see that the F statistic will just be ratios of those MSEs, or ratios of sums of squares divided by degrees of freedom, which is what we know F-test should be. Alright, so I'll let you think about how to fill in the rest of these, and I will fill them in and post the notes, but I think it would be a good exercise for you to to fill each one of these in, and that would require that you develop some notation similar to the notation here, but I think it should be pretty self-explanatory. Alright, the main thing that I want us to take away from this table, though, is that the p-values in the rightmost column are testing important null hypotheses and basically testing the difference between reduced models and full models, and so being clear about what those models are is really important. So what does this look like coming from R? Well, here's a screenshot of the data that we'll look at in the next video, and we see, numbers put in for the degrees of freedom, sums of squares, etc. And if we look at the p-values in the last column, then we see small p-values for both. So this p-value here, again, tests the model with no predictors in it at all, so no blocking factor, no treatment factor, against the model with just the blocking factor. And we see that that p-value is small, so we would reject the null hypothesis and conclude that we at least need the blocking factor. Now the next p-value, this one here, is testing the reduced model that includes the block but not the treatment against the model that includes both the block and the treatment. And again, here we see a small p-value, which suggests that there is some difference across the treatment factor. And so this is our last video other than the data analysis on the next one, where we will study experimental design. We'll be moving on to generalized linear models and generalized additive models. So I just wanted to mention, where we might go from here if we were to continue a study of experimental design. And that way, if you find yourself in a role where you need some more complicated experiment, maybe you have some sense of what to do. So you might have two blocking factors. There's no reason to think that you should just be limited to one. And a Latin squares allows you to take two blocking factors into account. You might also have two treatments with an interaction. And we looked at this a little bit. In this case, you have a factorial design, and so we talked a little bit about full factorial designs. And then you could also have a 2k factorial design where there are k factors, each with two levels. And there's lots of literature that I can direct you towards to study these sorts of designs.